Okay, welcome to the discussion about the architecture. So the intention of this module is to just discuss kind of the architecture at a high level. Um, the kind of the rough outline I have for this is we'll kind of scour back through the main program and we'll look at what all is comprised in the main program. We'll look at device hierarchy. So we'll look at how we define devices in a system and in a cell, and then how we determine which one is the commander and which one's the follower. And then I may get into some aspects of how we declare variables to be used globally and a couple different methods that we use to do that. My intention is not to be super long in this discussion, but I do have a feeling it might be long. Um, so let's first pop open the Codesys code and take a look. I have the main program open right now. So if you see this program right here, main, um, at the top here we have our variable declaration. Um, and then here we have just simple three ladder rungs, which basically call the entire logic for this whole system. So starting at the top, I have the system config function block. Typically, this allows us to set some configuration parameters for how the system is going to behave. Things like developer bits, dry cycle. There's certain things in there that you don't want to change frequently. You just want to configure it at the beginning, and um, so all those sorts of things are housed there. In the second rung, we have this sort of system level function blocks. These are the function blocks that don't apply to a specific device within the cell or the region. It just kind of is something that just belongs to the machine itself at the very top level. These are things like managing the clock, the time, the I/O map, um, network manager. This is just detecting the connection states of all of our different Ethernet devices. Um, Utilities function block. This is providing a lot of goodies for us to use all throughout the code. Things like a first scan bit, which comes stock with Allen Bradley. I didn't really look to see if it comes stock with Codesys. I just created my own bit, but super useful. Other things like flashers. So these are things that are on for 250 milliseconds and off. Same thing here. So some of these different utilities are just kind of nice to use. Always on, always off bits. Um, yeah, aside from that, I'd say the big hitters, probably the recipe manager, um, and also the fault monitor function block. The fault monitor function block collects all of the faults from every device and this actual system level device as well, and is responsible for like collecting those into one succinct list of errors and warnings. Um, Something like a light manager, the stack light manager, motion permissives and overrides. Um, this is kind of the first defense in programming a machine so it doesn't run into itself. Uh, you know, Engineers can have a habit of designing things eloquently, but may forget during debug to check for this, that, or the other. And this is just an easy way to manage those permissives in one location, and it's really just intended to protect engineers from themselves if they write some bad logic. So yeah, other than that, safety function block. This just performs most of our resetting um, functions. This isn't a safety PLC, so all the safety performance level logic that's housed in our safety controller in that firmware, which is pretty simple logic. But this safety function block basically just um, governs whether or not we allow something to be reset or not. And typically, we're monitoring the normally closed states of um, the safety contactors and of the dump valves. So that sort of logic is housed in here. Um, I may end up doing more of a detailed sort of video on some of these specific function blocks, but some of the logic here it's pretty damn simple to follow along. So as you kind of dig into the logic yourself, you can kind of look and see what it's doing. Um, so noticed for this function block, I don't have a description comment. So these description comments are nice. When you hover over something, it gives you a description of what's going on inside. So I think I'll just say for now, reset logic for e-stop and fence circuits. It does some more things than that. Also, I guess fence guard door locking as well. Um, yeah, and just some other diagnostics. So now when we hover over function block, safety function block, you see it included that comment. Thank you very much, Codices. All right. Back to main. So yeah, there's just a handful of kind of function blocks that just don't, they don't belong anywhere in any specific device. They just kind of belong to the system. So that's kind of the point of the system level logic. And then basically everything else is kind of housed in this kind of conductor field. So we've got a mode manager function block, which we'll see really acts as the parent to the conductor. And then we have this conductor function block, which houses all of the devices that we're using, like the robot device, the CNC device, all that. And then those devices within the devices, like a Russian doll. So let's go ahead and segue into um, the PowerPoint, and we'll take a look at our device hierarchy here. So at the very top level of our hierarchy, we have this system level device and the safety level device, and basically they just sit at the top. Really, everything is primarily governed by the safety. If you think about the operability of a machine is highly dependent on whether the e-stop circuit is healthy or not. So that's kind of why we put the safety in the system and all that kind of at the top. And then there directly under we have the mode manager. The mode manager would allow us to kind of switch gears, and if typically in systems that I've worked on in the past, mode manager does more than what it does in this system. I think I've thrown in things like the dry cycle, different sorts of activities like purging, um, just sort of like really high level sort of operation modes that the the user wants to use. That the mode manager would kind of help govern whether or not we could switch gears with what the machine's current state is, and if it, you know, for example, can you jump from auto mode to a manual mode? Well, the mode manager would govern that, and typically it wouldn't allow that type of transition unless, like the system was stopped and everything was kosher. Um, with this system, the robot really kind of governs the whole show. So if the robot's in teach pendant mode, for this system, I've just kind of geared it to kind of react to what's going on with the robot, because not a lot of things can really happen without the robot being up. But certainly the provision, the architecture would allow someone to de-emphasize the robot and kind of employ some more strategic mode switching. Some other cases of like different modes I've seen in the past, we've had this like daily inspection mode where the idea is that, the machine has to be completely empty, and then you load in these, they're called like MVP parts, but they're basically just parts that will either pass or fail, and the failure mode. And when you send them through the system, you're expecting the system to error out in a certain pattern. Um, and so that type of mode um, would, that's just another example of a mode. You'd use like very much the same set of automated features that the auto mode is doing, but you kind of do them in a different way, or maybe you don't finish a certain task because it may damage an MVP part or something like that. So the mode manager just kind of allows us to change the flavor of how the conductor is issuing commands. So, like I said, in this system, we don't really have that. We kind of have an auto mode and a manual mode, and like I said, that's kind of governed by what the robot's doing. So maybe in the future, if there was some expansion on adding some more modes, certainly it's the backbone is there, and the logic could be inserted. So the mode manager is usually in direct communication with the HMI. I probably should have depicted that right here, but the HMI is, let's go ahead and do that right now. I usually like to throw that in there. So, the HMI is really our human in the loop. So, um, not a lot of action is going to happen unless the human is hitting buttons and telling the system to start or stop. So, oops. So there we go. So yeah, the HMI, will talk back and forth with the mode manager. It'll, a user will hit a start button. The mode manager will then say, is it in the correct state? Is the mode manager in the correct state to respond to start commands? If it is, then it'll issue a start command down to the conductor, and then it's kind of a chain reaction down the line, down the chain of command. So the way that this hierarchy works, it's like a top down cascade. So the action starts at the HMI with the user, and then the mode manager issues down the conductor, and then the conductor issues down to its children. So in this case, the conductor has 3 children: the CNC, the robot, and the rack. So then the CNC gets the start command. It issues down to its children, and it has 3. This FANUC Zero Eye controller, it actually has more than 3. This FANUC Zero Eye is kind of the primary sub device of the CNC. The rest of these are just kind of simple 2-position devices. There's 1, 2, 3, 4, 5 2-position devices, which are very like primitive devices. Devices nonetheless. Then you got the robot, and it has its children. It has a deburr washer. its own robot controller. And then it has these primitive left gripper, right gripper devices. And in this case, those devices in our system are just monitored. The robot controller actually controls these, but we are able to monitor the states of that with these here, and we'll get into that in a little bit greater detail. Then I have this rack device, which manages the rack, the raw shelf and the done shelf, and allows us to edit the rack shelf parts, things like that. So, um, but yeah, basically from this, hierarchy, like I said, it's kind of a top down as far as the command structure goes, and then, errors kind of work themselves kind of top to bottom, as far as the reaction goes, and we'll get into that probably in a future video, but we'll kind of see how the chain of reaction um, is described when we're triggering faults in the system. Um, so I think with that, I'm going to jump back and um, yeah, I just want to make sure I'm being clear about kind of devices. I'll just maybe speak to I'll just speak to why I discretized the system into these device groups. Um, and I think given the opportunity to refactor the code, I perhaps would simplify or reduce some of these. But I really tried to, when I first attacked this problem of developing the system, I tried to give myself the most flexibility, and the most flexibility meant creating more devices as opposed to creating less. So, the sort of spirit of building one Doosan 8 work cell was to be an experimental test bed to not only kind of test the our original, quote unquote, original design, or our best foot forward, but also to have the ability to adapt. And talking with the owners had some concepts and ideas about maybe how the the robot cell maybe would include some additional devices, um, that we would add in at a later date. And so it made sense to kind of organize things this way, because we wanted to have kind of the ability to add additional devices and to kind of um, mute the devices, or not allow a certain device to be active if a certain cell didn't contain that device. And so kind of wanted to create an architecture that would allow us to disable and enable certain devices or certain processes within a work cell. So um, the the way that I chose to dissect the system, um, I tried to separate things in a way such that I wanted to limit the conductor's communication to low-level devices. The conductor is really kind of like, if you think about like in a business organization, it's like the manager. He doesn't need to know the specifics of what you're doing from day to day. He's just more in charge of the big picture. And so, the conductor, he really just wants to issue high level kind of tasks, and allow its children devices to kind of distribute those down to like the low level control, like physically setting an output on an SMC valve, for example. So the idea is that, the task and the conductor, should read, it should read pretty cleanly to anyone, to anyone walking up to the project, whether or not they understand automation or not. They should read the task, and with minimal um, and kind of orientation to, what the work cell actually does. A person should be able to kind of pick up and see what's going on, like, oh yeah. And we see that with the task planner. When we populate that task list on the UI operator screen, it's should be kind of easy for most to understand what the hell is going on and what's going to be happening. But drilling down deeper, once I have these kind of big, children of the conductor, uh, digging down deeper into them, I chose to further discretize them, specifically the CNC. Um, a lot of, I would say more so than the robot, the CNC is probably one of the cases where I could see us really utilizing this sort of discretized architecture, because the idea is, I want this CNC parent device. I want it to behave and act in a very consistent manner relative to the conductor. The conductor and the CNC's communication back and forth with one another should be identical, whether the CNC uses a FANUC 0i controller, it uses a Heidenhain, whatever. But I want to keep the communication between the conductor and the CNC very consistent. So um, that way, if you adapt this logic to another system, um, you really just kind of have to drill into the specific low-level control of the controller itself. And so, in this architecture, the idea is that you would rip out this FANUC 0i CNC controller device and put in, say, a Heidenhain device and write the logic to that. Um, so that's kind of the spirit of this architecture, is to be able to rip out. You kind of want to abstract out the low-level details of what's going on behind the scenes. Like, this CNC parent device doesn't need to know about the specific, input and output bits that are being set between the PLC and the FANUC controller, all that handshaking. It doesn't need to know that. It just can say things like, hey, I want you to change the program to this program number, some very high level, or start the CNC program. Tell the CNC program it's loaded. Tell the CNC program we picked it. Finish the CNC program, like let it execute to its end. Um, so yeah, the idea is we want to kind of minimize the amount of data that is used amongst, like a parent device and a child device, and keep the communication lines restricted so that, it's only using what it absolutely needs to know to make sure that it can properly function. So that's kind of the idea behind that discretization. Obviously, with different CNC setups, this discretization may not make sense. And the other thing I didn't talk about here was this fourth axis control. So this fourth axis control, the CNC is basically controlling the tailstock positions and the expanding collet positions. And I think in future iterations of this work cell, the fourth axis controls will actually kind of be housed inside of the FANUC 0i CNC controller, because I believe the idea is to move the valve hardware that we have on the SMC and actually roll that into, valve hardware that's tied directly to the CNC controller and is only accessed from the CNC controller and must be requested by the this by the PLC to the CNC controller to turn on the tailstock or extend it or retract. Um, in our current system right now, the CNC is actually able to control those valve states. So hopefully I know I'm using the word CNC interchangeably here, but hopefully it's clear what I'm talking about. So, and similarly with the door, it sounds like the idea is we would move the door controls into the FANUC CNC controller. So in the future, this sort of device may merely just consist of the CNC and then a FANUC 0i V2 CNC controller. Um, Controller device. So similarly on the robot side, have this FANUC robot R30IB controller. It's feasible that we may not go with FANUC in the future. I know that's highly unlikely, but if you ever did, or if you had a different version of a FANUC controller, you could swap it out with this device, and everything else should kind of play nicely. Um, the deburr and the wash both have their own dedicated devices, and it's like a full device, so it's got state engine logic. It's like a state machine. Pretty overkill for what we're doing. But I thought, at least when I originally was thinking about this architecture and I knew a new controls engineer would be coming on, I originally kind of had the idea that I could really teach someone easily how to create and develop a new device by working on something simple like the deburr or the wash. Since it's only like you're only setting one or two outputs respectively, the device logic will look very simple, and so it might be easy to kind of hold someone's hand and allow them to say, hey, why don't you try to follow my architecture and develop the deburr device, and then we'll see how you did, and we can talk about it. And it's not this big complex monster like the FANUC 0i controller, or something like that. So, or the robot or the CNC level device. So that was kind of the idea of why those particular things were devices. I think if you really wanted to just strip it out, probably a person could just probably strip it away and just do something like I think just you could probably just directly set the outputs for the deburr and the washer from the robot. You would just include those as robot outputs in this scheme. But yeah, that's not how I did it here. So the left gripper, right gripper, two position devices that I have in the cell are just monitoring the output state and the sensor state for the left gripper and the right gripper, and issuing warnings and errors related to that. Like, if I can tell if the robot, opens its gripper and I can see that the output state is on and I don't see a sensor reflecting that position, I can trigger a warning, um, to the system. And that's useful for diagnostics. So it's nice to have that, up, and I can, it's really a good use of, how the architecture kind of works and how error management and reporting and all that kind of works. It's pretty simple when we really drill down into kind of the anatomy of these devices, and we talk a little bit about um, the data flow of like commands coming down, error monitoring, reporting states back, we'll kind of see the behavior of all those things is consistent no matter which level in the hierarchy you are. And so it really kind of simplifies, um, it does simplify the logic because it does become a little bit, it becomes kind of cookie cutter at a certain point. So you don't have to rethink the wheel on how to handle error reporting and all that. You just kind of monkey see, monkey do, cut, copy, paste, just follow the formula, follow the pattern, and repeat the pattern. Um, so it is kind of nice. It does reduce, while it may take a little longer to set it up, it does, I guarantee you, it does reduce the mental strain aspects of coding because it's already done, already been tested, already proven. You don't have to think of a new set of rules by which to follow. You just follow what's already been given. So um, that is kind of the theme in general for this architecture. It's meant to have a high degree of both pattern and flexibility. So I know that oftentimes those two things compete. If something is highly flexible, typically it does not necessarily follow a pattern. But I um, try to optimize um, the ability to kind of modify and customize specific devices, um, while also keeping you know, let's call it the backbone features, the error reporting, the state reporting, keeping that consistent. It certainly helps. It helps you as a developer jump into someone else's code, and as long as they're following this guideline of, okay, these states indicate this general thing about your device. Like, it's assumed that when you're in an active state that you're not moving, your parts are dead, you're not dead, but you're not doing anything. You're not ready to go. You're not your drives aren't enabled. You're inactive. You don't have the ability to perform real tasks yet because you haven't been initialized, reset, and prepared yourself to be ready to run and in an idle state. So um, I think that is something that consistent state management is definitely, it's nice to have a translation between, when you get down to, however the FANUC 0i folks wrote their firmware and they define their own states. um, it's nice to have a translation layer where you say, even FANUC may call their idle state, it might be like a combination of three different things. And so if you can kind of combine those down and boil them and reduce them down into, it's like, okay, well, I can tell the CNC parent that I'm idle. Well, then, I've simplified the communication. And um, yeah, I think it just helps. I think it helps you as a developer jumping into someone else's code, um, to already have a level of understanding of how their device is going to work. So I think we'll dig in on the next videos. We'll start to actually dive into the anatomy of the device and talk about the states in detail. Um, but yeah, I think going over this device hierarchy and showing you how the symphony of devices work with one another and how they really follow, the conductor who's just only interested in the bulk and the top level tasks that are happening. I think it's important to kind of understand how all this works and how the chains of command all kind of work. So As I go through the next videos, I hope to diagram as well kind of what specific commands conductor gives down to the CNC and what CNC gives down to FANUC. Like I hope to kind of define some sort of interface slides to show, to show you that, to diagram you that. But I think for now, this is at least a solid introduction into the architecture. And with that, I will sign off.